Um, yeah, I think that's an old biography that we had lying around on our website, so apologies for that. But so my name is Julien Flack. I'm from the Perth office of Dynamic Digital Depth, where we have our research and software engineering divisions. Today I'm going to be talking about an architecture for high-performance game rendering on Android. So just briefly, I'm going to talk about really the context and the architecture of our gaming technology as it's integrated into the Android operating system. I'm going to talk about some stereoscopic rendering techniques that we've developed to particularly address performance issues, look at some results, and then talk about some of the directions we're taking this technology in on Android and on other platforms as well. So, it's interesting to hear Nick's comments about gaming. I think from our perspective as a company, as a commercial company putting products out there, one of the key things that we feel has been part of the sort of 3D evolution has been a lack of really compelling content. Although there's a great deal of 3D content that's out there now, it still seems like something that's held back the industry. At least that's what many people sort of propose there. And from our perspective, gaming provides a really great source of 3D content. It's very high quality. It's designed effectively for 3D, although it's rendered onto a 2D display. It's a great way of unlocking content, and we feel that the sort of demographic of the people that do gaming fits quite well with Stereo 3D. So it's an area we've spent quite a lot of time in because we feel it can drive these commercial solutions for us. There's been some studies about the effect of 3D gaming, and obviously Nick's been very active in this field. But I think the benefit has been more about the increased immersion and the sort of more natural interaction. I think, in fact, Shield, who's authored one of those studies, sort of indicated that perhaps in terms of improved scores, there wasn't, that wasn't easily pinned down in the sort of common games. Because of all these other effects that are going on as well, but certainly there's a sense that there's more immersion and interaction in the game. So as I said, we've been doing this for quite some time. We developed stereoscopic rendering technologies for going back as far as DirectX 7, and we've done 8, 9, 10, 11, OpenGL, and so we've been involved with that for quite a while. We've successfully commercialized that technology. Our licensees included initially Sharp, and then Samsung, LG, and Intel have all licensed this technology from us. So, just in terms of the context of where we're going with the Android architecture, which really we're building on from our PC solutions. So the Android ecosystem is fantastic for gaming. There's not any tablets and mobile phones that run Android. There's now smart TVs, particularly coming out of China, that have Android cores embedded inside the TV. There's also set-top box, or these TV sticks that are also promising to bring new ways of enjoying games on many different types of screens. And associated with that is these sort of new interaction mechanisms that we have, like Mirrorcast, which enables you to wirelessly connect a mobile or a tablet to a 3D TV, and so that you can play in 3D from a 2D device, and that's an area we're very excited about. And also there's wireless controllers like Bluetooth that are becoming much more popular in the gaming platform. And also the level of performance that you're getting out of Android processors now is sort of reaching the console level. So it's there's a lot of positive factors in this environment. And at the moment, there is limited support for stereoscopic 3D within Android. Obviously, NVIDIA and Tegra have one solution, but that's sort of proprietary to their chipset, and there's a need to sort of bring this to other processors and chipsets. So for us, the architecture, what we were trying to achieve was to convert existing games into 3D. In other words, we didn't want the game developers to have to integrate stereoscopic effects into their game, because that can be, particularly from a display vendor or a tablet manufacturer who wants to be able to support 200 games in 3D, the length that would take to achieve, or the effort involved with that, would just make it unfeasible. So really the objective is to be able to convert things to 3D. We targeted a OpenGL ES compliant solution so that we can put that on any processor that supported OpenGL. At the moment, we support 1.1 and 2.0. We wanted to be able to support a wide range of games and also interface with a lot of different display types. So this is, if I can get this to work. So this diagram tries to illustrate the Android operating system and where we fit into it. So at the application level, you launch a game from our interface that then launches the actual game, and then we redirect the graphics through the driver level, which really does all the hard work in terms of converting to 3D, and we use obviously the system OpenGL library to then render that. In some cases, there's a system 3D API that we interact with. For example, on tablets and mobile phones, sometimes you have to switch a barrier on and off. On TV systems, you may have a frame sequential system, so all of these things are controlled by a low-level API. A key component for us really is being able to support all these different 3D display types as well. Because we want to be in different parts of the ecosystem, we want to support shutter glasses, even glasses-free systems, multi-view, as well as even head tracking and so forth, and we've done all of those within the framework of this architecture. So in terms of rendering techniques, there's really three approaches that you can look at within the framework of this architecture. The most traditional one is the virtual camera offset, which is just effectively a stereo render. I'm not going to sort of go into the details because I think probably most of you are aware of all those different techniques. But effectively, you're rendering the scene twice, or parts of the scene at least twice, with an offset between two different camera positions that can be configured in different ways. The second technique that I'm going to talk about a little bit today is layer parallax, where you really just shift layers of the scene relative to each other, and it's a much more simplistic 3D effect. And then finally, there's also depth-based image rendering, which is a technique that's very close to our heart, that's a core component of our PC graphics driver, and something that we've been investigating within the Android framework as well. Performance is always a key issue for gaming, for 3D gaming, obviously alongside quality, and the two kind of interact in complex ways, but the performance really is the key thing for gamers who need high frame rates. For interleaved displays, which are relatively common on glasses-free 3D display tablets and mobile phones that generally use vertical or horizontal interlacing, there's a method called stencil buffering that's been out there for quite some time that allows you to do that much more optimally. Rather than rendering a left eye and a right eye and then interleaving them, you effectively only need to render the pixels for each interleave separately. So that's been around for a while, but when we came to apply this within the Android framework, we realized there were some issues relating to games that already use the stencil buffer for other effects, such as shadows and reflections, so forth. So we developed a new technique that overcomes some of those limitations called depth stripe rendering. So in outline, how this works is within the graphics pipeline, there's a stage that's a fragment shader or pixel shader, where you decide which pixels are actually going to be displayed on the screen. Might need that pointer. So effectively the technique pre-initializes the depth buffer in an interlaced signal. So we may set, for example, the odd lines, and this is a horizontal interlaced example, may set the odd lines to 0 and the even lines to 1. And then as we go through the render loop, we modify the depth test. Thanks, Steve. We modify the depth test so that when we render the object intended for the left eye, we only need to render the pixels that have been preset by this interleaving in the buffer. We then change the depth test and change the range of it so that when we render the object for the right eye, we only render the pixels that are appropriate to that particular line. And obviously you can change this pattern to vertical interlace, checkerboard, anything that's an interleaved pattern. So this is a technique that we have been investigating for more performance improvements, and I'll come back to some performance figures in a little while. The other problem that we came across when we looked at Android was that we found that many very popular games, casual games, didn't actually use 3D geometry. They were rendered onto a flat plane. Angry Birds is the classic case. There's others like, Bad Piggies and Amazing Alex and Plants vs. Zombies along those sorts of lines. So that presented us with a bit of a sort of practical challenge, I guess, is how to convert these games into 3D. So we wanted to include that as part of our architecture. What we came up with is it's not 2D to 3D conversion based on the image data, because we're in the graphics command pipeline, so that effectively we already have a pre-segmented image, or at least we can strive towards that. But what we developed as part of this architecture is a domain-specific language so that we can identify and track individual graphic elements. And we have game-specific rules that trigger on key events, like on draw calls and on clear calls, so that we can identify which part of the game we're actually rendering and modify the position. So this is, I've mocked this up just in Photoshop, but you can see we've basically got a sequence of 4 or 5 layers that we've pulled out of the game, from the background to the sort of physics layer in the middle, through to some of the foreground, and then obviously the on-screen displays is on a separate layer. And we can shift these layers relative to each other to optimize the game. And we do this on a game-by-game basis, so we have a sort of rule set that plugs into this architecture and allows us to convert these games. Obviously, it's not full 3D, but in practical terms, when a company like LG or Lenovo wants to have a solution, they want to include these very, very popular games. So we needed to find a solution to this problem. And you do get some pretty good effects from this. So in terms of performance, going back to the depth stripe rendering, we used a standard Android benchmark called 3D Mark. This is the Ice Storm render. We ran this on the Hampu 3D tablet that's based on a TI map processor. The benchmark is really a high-end benchmark, and it struggled a little bit on this particular process. So you can see the frame rates are relatively low. You wouldn't really want to be playing a game below sort of 25 frames per second. But for us, the aim was really to look at the relative difference between the 2D render, the depth stripe render, which is one on the bottom, and the more traditional stencil buffering. So you can see that the depth stripe render and the stencil buffer are effectively, in lockstep, and provide about 20% overhead compared to the 2D render, which is pretty reasonable, because in a lot of cases to render stereo, if you're rendering the scene twice, you have as much as 100% overhead. So that's not bad. It shows that the depth stripe approach mimics the stencil buffer in terms of performance, and it doesn't have some of those disadvantages that I talked about. So to look at some performance figures for some games more generally, to give you a sense of how that pans out in practice when you're playing games on different platforms. We've got 3 different systems. This is a Neo 3DO tablet. It's an auto stereoscopic tablet that some of you may be aware of. It's based on a fairly sort of lower cost, I guess, processor. It's an AM Logic dual-core A9. And then we got Samsung Galaxy S4 phone, because the reason we tested on this is because one of the use cases we're very interested in is using a 2D device to drive a 3D TV. So many people have 2D phones. They can easily now get those to render onto a 3D TV using Miracast or even a HDMI connection. Particularly if you have a game controller, it's a very natural way of interacting. And now that the performance of these platforms is high up there, you can see that that becomes a feasible thing. So in general terms, these top ones are the sort of layered 3D. We also included a Tegra-based TV board that we're working on. This is kind of a prototype. But just to show you that some of these new systems that are coming through as the Tegra 4, the frame rates are pretty good, both in 2D and 3D. There's hardly any overhead for the layer-based approaches, and not too much overhead in terms of 3D. So we get pretty reasonable performance across the board. I'm just going to skip through a little bit because I'm sort of running a bit short of time, but we are still looking at depth-based rendering. There's some advantages to that, particularly when you look at multi-view, but at the moment, the performance of Android processors, we find accessing the depth texture and using that as a render target has some overhead. So although the performance is roughly the same as depth stripe rendering, it's not something that we're sort of actively using on Android at this stage, but we certainly think it will be used in the future. We did some battery consumption tests. There's a bit more sort of detail in the paper, but effectively we use about, the battery lasts about 30% longer in 2D. Obviously we're doing some more processing there, just to give you a sense of that. In terms of future markets and where we're going with this technology, smart TV is really our key focus. And now that there's a lot of emerging Android systems on smart TV, that's really what we're looking at, including sort of ways of interacting with game controllers and other Kinect-style interfaces, if you like. Head-mounted displays, obviously, we already have solutions on PC for the Oculus Rift. We're also working with a company called GameFace. They showed this at CES. That was running our software to create 3D for their head-mounted display. And as I mentioned, we're looking at advanced rendering performance as the platforms evolved, both on ARM-based and Intel processors are obviously moving into the mobile space now as well. So just to wrap it all up, what I've presented today is an open standards-based architecture for 3D gaming on Android. And we've deployed that now on a number of different systems, and we're testing it on a few more. We've developed a new rendering technique to really address some of the performance issues and make sure that we can get the maximum frame rate. And we've also outlined a solution for converting 2D layer-based games into 3D using sort of game-specific AI rules. And that's it. Thank you.